Hello, everyone. I'd like to take a few moments to talk about some generative AI models and how they might be used to make some music in the browser. And, well, AI, deep learning, neural networks, when people talk about these things today, it is still too often that this is the kind of thing you see. It's kind of an area of active research with a kind of heavy crust of math and jargon around it, which is great if you are a researcher because you need a language to talk to other researchers with, but it's not so great if you're trying to kind of make things without actually being in the field so much. But that's all right because I've noticed this year that you don't actually have to know a whole lot about the core concepts to be able to do things. And I know this because I've been doing things without really understanding much of anything about this shit. And that is all thanks to abstractions. Abstractions are nice, and people have been making them recently. One of them is called Tensorflow.js, which is a library you may have heard of, came out earlier this year, lets you do GPU-accelerated math in the browser, in particular the kind of math you need to run neural networks, and gives you a set of nice JavaScript abstractions on top of this basic core math. Even more interestingly, maybe for this audience, though, there's an abstraction on top of that called Magenta.js. And this Magenta, if you haven't heard of them, is a research group within Google who are in the business of making AI models for music and art, musical and artistic expression. So they put out a lot of original research, put out papers, models, but they also put out software which then lets people like me use these models without having to really understand them in that kind of deep level. And Magenta.js is a recent example of that kind of thing. It's basically a wrapper for TensorFlow.js, which gives you a set of musically oriented abstractions around this basic AI tech, which then lets someone like me, who is a kind of a music hacker, to then build applications on top of it. And, well, here's one such application. This is an arpeggiator, which, when I press down some keys on the keyboard, will arpeggiate a melody around that chord for me. So let me just try that here. So whenever I hit my fingers on the keyboard, the neural network in here will generate a melody around those keys for me. And it's a different one every time I press my fingers down. That kind of thing. This is powered by a Magenta model called improv-RNN, which is not a simple model at all, kind of at its kind of how it worked internally, but the surface of it, if you actually just want to use it, is actually quite simple. You can actually think of it just as a function. It's a function whose purpose is to take the beginning of a melody and then generate a continuation for that melody. And in this particular model, you have two arguments you give to it. You give the beginning of your melody, and you give the chord structure you want that melody that's generated to stay within. And when you give those two arguments, out pops a melody that hopefully stays within that chord. And that's pretty much it. And a function, really, that you just need to call. In code, this is how that all looks like. So we have a Magenta music library. This is the Magenta.js library now, which gives you a music RNN class, which you can instantiate, and you give to that a URL to a pre-trained neural network model. And Google has a bunch of these available, so if you don't want to train your own, you can just use Google's, load them from their CDN, which is what I do in my applications. You initialize that, which will then pull that neural net from the internet, initialize it, which takes a while. These aren't small, these things. It might be 10, 20 megabytes or so, these things, when you load them up. So it takes a moment to load. When you have that, though, you can start using it. And you do that by providing it with a certain kind of melody seed, which you give as a data structure of a certain kind. The interesting point here being that these are MIDI pitches at quantized time steps. That's what this model will understand. You make one of those, you feed it into the RNN and say, continue this sequence for me, please. And you give it the seed, you give how many time steps you want to generate, You give the so-called model temperature, which will let you control how random you want those results to get, so you can increase that if you want to get more weird with these results. And you give the chord structure, or in this case I'm just saying, please give me everything in the C major chord. And that will then go into the GPU, run the neural network there, and when it's done, resolve this promise, give you a generated melody. And that's what I'm doing with the arpeggiator. I'm basically using the keys you press on the keyboard both to kind of form this seed melody and infer the chord structure as well. And I just call this single method, and the result is what you hear. And well, that's how you can make a melody with one of these things. You can do other things as well. For example, you can do drum patterns, because there are models for that as well. And here's a drum machine that I made based on that principle. It has really the same operating mode as the previous demo, where you provide a seed on the left here for what you want your sequence to begin with, and then you let the neural network generate the rest, which will happen when I click this button here. So everything in blue here comes from the neural net, and every time I click this button, it will come up with a new answer to this question of what should this pattern be. And I could do that all day, but let me just go forward here. This is powered by another Magenta model called the drums RNN, which is very, very similar to the improv RNN. It just takes a seed pattern of what drums you want to begin with and generates the continuation for that. And on the code level, it also looks pretty similar to the melody example. It's actually the exact same API. You just still make a music RNN, give it the URL to a pre-trained drum model. You provide your seed sequence with that same data structure as before, the difference now being that the pitches here aren't actual melodic pitches, they are drums, and this is following the general MIDI mapping of drums to pitches, so 36 is the kick drum and so on and so on. But still you use the same data structure to use this for both drums and melodies. And you use that same method in the end to generate. So continue a drum sequence for me for 12 time steps with temperature 1.0, and out will come a drum pattern. And that's what I'm doing with the drum machine. And those are a couple of examples of RNNs that Magenta comes with. There are a few other ones that I won't get into too much. Maybe most interestingly, there's one called performance RNN, which is interesting because it's trained not just on music as structure, but music as performed by humans. So it's trained on human piano performances. So it attempts to capture things like expressive timing and expressive dynamics when people play piano, and that makes it kind of come out with more human-like outputs as well when you generate things with that. And you can find a nice demo of that on the TensorFlow.js website, which lets you kind of play with that in the browser. But I'm going to use my remaining time to talk about something different than RNNs, to kind of give you an idea that you can do a bit more with these models as well than just continuous sequences, which is what I've been doing so far. And I'm doing that with my latest project here, which is called the Incredible Musical Spinners from Latent Space. And well, just going to show you how this works. There are two seed patterns here, single measures of music on the page currently, looping measures, which you may notice are actually multi-instrumental music now. This model is not just about single melodies, but actual multi-track music with multiple instruments, including percussion. And I have two of these patterns here, which come from the model. But then I will click play here, and the model will do some more work for me now, which is to take these two seed patterns and generate a whole two-dimensional field of music for me from these. And it will make an actual 7x7 grid of loops of this kind, where the left and right edges of the grid will be based on these two seed patterns. And then everything between the left and right edges is a so-called interpolation between those two patterns. So there's a kind of a stepwise morphing from one pattern to the next. And as you see, these things aren't exactly fast, so it takes a while to do all that work of generating, and now it's done. So if I start from the left side here and go to the right, there's supposed to be a kind of smooth transition that makes sense in a musical fashion from every step to the next, while at each step I will get further and further from the beginning point and closer to the goal or the end pattern. What I've also done here is that on the vertical axis I've done the same interpolation in 7 different chords. In this case, this is the key of D minor. So the same interpolation is going on each row, but on the vertical axis I can then do chord progressions. Things like that. Every single one of these patterns comes from the neural network, from that kind of neighborhood of music it found from those 2 patterns that I gave it. This is powered by a model called the Music VAE, which is short for variational autoencoder. And these are models whose point is to capture some information in a kind of geometric space. In this case, a geometric space of music. And so every point in that space is a single musical measure. So every one of those spinners from that application lives somewhere in this kind of vast space of possible music. And it is a very high dimensional space. This one is, I believe, like 256 dimensions. But it's still, so it can't really be intuited by a human being, but you can still kind of think of it as in geometric terms. And I'm here visualizing it as a 2D thing just to make sense of it, but it's actually 256D. But what you can do when you have a musical space, you can, for example, just randomly sample points from it, so-called embeddings or z-values, and say, what does that point sound like? And you can call a method called decode for any point, any coordinate point, and say, what kind of musical pattern lives here in that space? Every point will sound like something, because this kind of the whole point of this space is to model all possible single measures of music, at least those that exist in the training data. And so you can just randomly pick stuff, which is interesting, but even more interesting is when you have, say, an existing musical measure, and you can say, encode this for me, please. So it will tell you at which point in that space that particular piece of music lives. Because once you know that coordinate, you can do things with that information. For example, you can, say, mutate those coordinates a bit and see what other things are there in that neighborhood. Because things that are close to it in that geometric space should sound similar, but not quite the same. So you can kind of start exploring neighborhoods of music in this way as well. And if you happen to have 2 musical patterns, you can get 2 points by encoding both of them. 2 points in that space, and then you can walk the space between those 2 points and stop at certain intervals to kind of see what are the intermediate musical measures between these 2 endpoints. And that is the interpolation that I was doing in that previous application, where the 2 musical measures are the endpoints, and there's kind of this spacewalk behind those 2 points with decoded patterns at certain intervals, which give you the smooth transition. And these are the kinds of things you can do when you have a geometric space of music. You can walk the space, explore in different ways how you find different neighborhoods of music, how you connect different pieces of musical measures to each other, and so on. A very interesting thing to do. And, well, in code, this isn't really much more complicated than the RNN stuff I was showing earlier. You still use the Magenta.js library. You initialize this model called the Music VAE. You tell it where to find a pre-trained model, and again, Google has this available on their servers. And then once you have that, you can do things with that. For example, you can randomly sample points from the space. In this case, I'm saying, give me one sample with temperature 1.0 in the C major chord, and it'll pop out with a random musical measure. And you can do that interpolation thing, and for that you do need these existing musical measures for giving you the endpoints of the interpolation. And this is again the same data structure as before. This could be something you sample from the space, or it could be manually crafted, or it could be something you play on a keyboard, for example, and capture in this kind of data structure if you want to see what you can then do with that with this autoencoder. So you need two of those. You give them to the interpolate method of the VAE. It's got one handy for us to use. You say interpolate between these sequences in 5 steps with temperature 1.0 in the C major chord. and that'll give you a 5-point interpolation between any two musical measures. A really fun thing to kind of play with. And these are the kinds of things you can do with Magenta.js today. And I hope I've shown you can do them without really getting into neural networks at all. It's just a music-oriented API, really. So there are a number of different VAEs, a number of different RNNs available, pre-trained from Google. All of them use the exact same API I've just shown you. They've just been trained for different purposes. Some are simple melodies, some are multi-track melodies, some are based on drums, and some are human-performed sources. But all of them kind of follow the same principle of operation. And yeah, I've done a bunch of these applications this year. Most of them I have upon CodePen in that URL, the drum machine, the arpeggiator, and a few others you will find there, including the source code for them as well. And the latest one, Incredible Spinners, is on Glitch in that URL, and here are a couple of other ways you can reach me. And of course, I'll be available for the rest of the conference as well, and happy to talk about any of this. Thank you very much.
All right, we've got some questions rolling in.
Cool.
Interesting.
That's not me.
Let's see, so our first one is, what are some examples of what the axes in the musical VAE correspond to?
So, yeah, that's a good question. There are things called attribute vectors which you can train to do kind of meaningful musical transformations within this space. They don't usually fall exactly on certain axes, but they are vectors that kind of go through a certain direction in that space. And examples being note density, for example, so you can add more notes to a musical sequence by sliding a slider, for example, or note distance, like note intervals, or there's syncopation, and there's a few others. And these are all kind of found by the researchers at Google when they have their model, and then they kind of figure out what these vectors are by averaging out all the things that have syncopation, for example, and all that don't. And taking the distance between the averages of those gives them the vector, which you can add to any musical sequence to add, say, syncopation to a piece of music. But these kind of need to be found by usually the people who train the models, and then they make them available. So it's not that easy to kind of come up with them by yourself. You need to get extraordinarily lucky to find one.
I think that falls into the next one. Do we know what data GG has trained its models on?
Yes, I think most of these models are trained on the so-called LAC MIDI dataset, which is a huge set of MIDI files, essentially, which is open on the internet. And I think that's what they train, at least these VAEs on. So I think it's just most of the Western canon of popular and classical music that's available as MIDI files.
How could you inspire people to create music with your platform, or through this platform?
I mean, the things I think about usually is that for say, the arpeggiator or drum machine, they're mostly things like inspirational tools for musicians at the moment. So like people who are looking for some starting point for their creative process, for example. So the machine will just give them a pattern, which they can then use to kind of build their own things on top of. That's kind of, I think, a good way to do that. There are some people now who are actually starting to do a more tight collaboration with machines by training models on their own discography, for example. So a musician might do that and make a variational autoencoder, like embedding space based on their own previous music, and then figure out what their style is actually, and have the machine kind of improvise in their style, and which is a very interesting thing to do if you do have an existing discography.
And then can your work be easily integrated into external software? Can you like add an arpeggiator to a synthesizer, drum patterns to a drum box, etc.?
It could. Personally, my code base that I do in JavaScript, I've just recently tried to add MIDI input and output, web MIDI input and output to most of these, so you can just get MIDI in and out to any of these, including the MIDI clock, which lets you sync them to whatever time source you have. but all of my stuff is basically in the browser, so whatever limitations there are there exist. Some Magenta has done things like the so-called NSynth project, which is a plugin actually that you can use in something like Ableton Live, and just use there, which is no longer a web thing, but just a native thing. But it's just basically these neural networks are nothing but tens of megabytes of magic numbers, so you just need to kind of hack out some code to plug it into anything, really.
We have an update to that. How easy is it to connect it to just traditional new web audio instruments?
Pretty easy. I mean, that's what I do. The sounds I make are all based on just Tone.js, and I take these symbolic MIDI sequences that the models come out with and turn them into tone sequences or tone parts, and just then trigger audio buffers based on them, basically.
There's one more question, and it's fantastic, but way too long. You're going to have to ask this one. I'm just going to put it out there, and then we're going to have to go, and you can all think about it. But what do you think is the missing link from where we are now to true AI artistic expression? Grab him at lunch. All right.
Thank you very much.
Come on over. Thank you.